Hey tech heads, I'm Tech Ed Kersch, and I help tech-savvy people understand electronics and tech so they can design their own technology without spending a bunch of time and money figuring out all the engineering on their own. In today's video, we're going to step through this typical process to lay out a printed circuit board, but for the USB Type-C connector and for high speed, so USB 3.2, 10 gigabits per second. In this example, I'm redoing an existing USB hub sold by Texas Instruments, with just a little modification. Oh, and by the way, if you want access to the show notes or design files, comment me below and I'll send them to you. I'm doing the design based on this board below, and I'll be using Cadence Orcad software to do it. Cadence Orcad is a PCB design software, very advanced. It's made by Cadence Design Systems. Cadence Design distributes their software through what are called channel partners, and one of them, the major one in the US and for other locations in the world, is called EMA Design Automation. They're located in New York, and that company is the sponsor of this video. They allow electronics engineers to design the technology we enjoy today. From companies like Apple Computer, they're like my favorite hardware company, Intel, Samsung, you get the idea. In fact, they use this exact same software, a big brother to Cadence Orcad called Cadence Allegro, to make this amazing technology that, you're probably watching this video on. As electronic systems become more complex, the need for accurate PCB layout, PCB stack up, controlled impedance, and signal integrity analysis increases. To ensure reliable system performance, designers must account for crosstalk, reflections, and other factors that can degrade signal quality. All right. So what is signal integrity and why is it important for PCB designs? And why is it important? And for this design, I'm going to show you that I did. Signal integrity is a measure of the quality of an electrical signal. It's important for PCB designs because it affects the performance of the overall circuit. And by using the strategy I show you in this design video, this will help you ensure that your USB-C and USB 3 layout is done. Now I'll demonstrate to you how to do a PCB layout for high-speed digital design of the USB 3.2 protocol using USB-C connectors. Okay, so initially the first step would be design and conceptualization. You want to conceptualize the design, think about what you actually want to. Now that's already been done for us, so that first phase is completed. The second phase would be component selection. So we have to ask ourselves some questions. What kind of controller we would need for the USB-C connectors? Okay, making sure that we can deliver the power needed. So if you need to charge, say, a laptop like my M1 MacBook Pro, for instance, then you will want to accommodate 100 watts of power. And if you need to go higher than that, then even 240 watts of power. The designer also ensures that the controller can deliver 10 to 20 gigabit per second speeds. So like for this USB hub, we want to be able to accommodate 20 gigabits per second, although at minimum 10 gigabits per second speed. And then that likely means that you have to take signal integrity and possible reflections into account and treat your traces as transmission lines on the printed circuit board. If you're not familiar with the USB 3 protocol and the speeds that it operates at, then you might want to check out the video where I explained that. Along with component selection, engineers take into account part availability. So especially in a silicon chip shortage, which has died down, you want to look at voltage operation levels for your part, communication protocols, connection types. If a controller can connect to a certain microcontroller chip that's talking to the main motherboard, or if it can't, or if it supports I2C or PCIe, or it just depends. Whether the devices are like compatible in terms of their communication protocol, like I just mentioned, if they need pull-up resistors, if they're internal, external, and if everything meets standards for reduction of hazardous substances, also called RoHS for short. You have to look at packaging, and since each part comes in various package types, like what footprints and sizes you can accommodate, whether they're going to be surface mount or through hole. You then have to organize the files and information about the parts on your computer. Then you go on to the next phase, which is the parts library maintenance in your design files, and how you would actually create the models yourself after you've selected the parts. But I don't recommend that. You want to mostly download the parts Okay, since we're talking about components and parts, the next phase would be modeling those components in your design software. All right, so once you have your part selected, you need to create files that model the various domains of any particular device. For instance, let's break this down. You have the schematic symbol, which represents the high-level functionality of that part within your overall design. You then have the SPICE model to simulate the circuit behavior within that same design. It's like running code for that part to make sure it works the way it's intended according to the datasheet. You also then have IBIS models, IBIS, and this stands for Input-Output Buffer Information System. Okay, so this is a model to simulate behavior in response to changes in design frequency and temperatures. And this is what you'd use to model the high-speed behavior, and also use this to export to third-party software to validate your process. But you don't have to with Cadence Allegro. More on that in another video. Okay, the next domain would be PCB footprints, to model the area underneath the part once it's actually laid onto a printed circuit board. So that's where you would get PCB footprints to model that. And then you have 3D models, so we know what the part looks like, and so that it's more realistic. Nowadays, you definitely have to use 3D models to verify that your part will fit properly, not just on a printed circuit board, but within the overall design and the form factor. Okay, so once you're done collecting all of your files, creating the files to model the parts that you selected, then the next step is capturing them in a schematic in your design software. So what you do is use your preferred PCB design software to generate a schematic. In this case, I'm using Orcad Capture, which captures the schematic. And the higher the speed of the design, the more powerful you want the software tools to be, because they account for more things, because they make your life easier and can handle the little nuances and errors easy to miss by having design rule checks, by having signal integrity analysis in the schematic phase even. So things that really give you a safety net when you're designing boards that can get pretty expensive. Once you're done capturing the schematic for the entire design, connecting them with the wires, validating and checking there are no errors, even setting your constraints in the schematic, combine all of your information like your component footprints, the 3D models and everything, and then generate what's called a netlist. This netlist will then be used to export your schematic concept to the printed circuit board in the mechanical phase. But before we continue to the next phase, here's my philosophy on schematics. Whether you're a hobbyist or working professional, I believe that schematics should be a document that encompasses all aspects and appeal to all stakeholders in the process. So programming notes for developers, firmware notes for firmware engineers, notes for standoffs and other mechanical items for mechanical engineers, and especially notes for the design, whether it's trace widths, component placement, and spacing notes for the PCB designer. In addition, including constraints on the schematic side if the schematic capture tool can hold design constraints. And then, of course, a bill of materials and everything else that you typically do with a schematic. Okay, the next step would be PCB Stack Up. I always tell my students when I give them formal training in printed circuit board design that you want to make sure you manage the stack up properly. It's not how many layers you use on a PCB Stack Up, not just the number of layers, but how you use them. That affects your electromagnetic compatibility, your electromagnetic interference, and ultimately your signal integrity in all fronts. Make sure you choose the right materials. In this situation, we chose materials that have a relatively low loss because we are going at high speed. Although, to be fair, it's more so losses from higher frequency and roughness of the copper that are going to affect the signals and attenuate the signals more than just the dissipation factor. So you want a PCB that has a good dielectric and is smooth as far as copper is concerned. You also want to see if you can get dielectric material that has good, consistent, like fiber weaving, that has tight weaving in there, because depending on how tight or loose the weave is, that's going to affect the signal integrity of your signals going through your PCB traces. So you have to work closely with your manufacturer to get the get the PCB stack for signal integrity and EMI and everything, especially for high speed like USB 3, USB 4. Now, if we pull up this guide here, there are strong recommendations for the length that you're going to run your trace, the maximum length, also the width of the traces, the space they need to be away from each other, depending on of course, the dielectric and PCB stack up that you chose it. So actually the thickness of the PCB, the dielectric layers, and also the copper, they all affect the impedance of your trace. If you want to control the impedance, make sure you have your stack up done first and that the trace widths and the spacing are within manufacturable limits, while also having them meet the recommendations and or requirements, like for instance what Texas Instruments has here. We're going to go with 95 ohms according to Texas Instruments recommendation for the SuperSpeed SSRX. Like these are the differential pairs on the USB 3. So this is why the PCB stack up is so important, because unless we do that, we're not able to meet these required. Like we don't know what widths to set our things at to meet these impedance requirements. Okay, now that stack up and impedance calculations are all finished, you want to do your constraints. So there's a whole heap of constraints that need to be taken into consideration for design for manufacturing, design for assembly, design for fabrication. You need your design for fabrication constraints that you would get from your manufacturer to see what are your minimum trace widths that you can work with. In fact, really you should be looking at this before you even set your impedance and trace widths, because that affects what the manufacturer can do as well. I've set it so that my trace widths don't go below 4 thousandths of an inch or 4 mils. There's also spacing, so making sure your components are not closer than your manufacturer can handle for whichever soldering process they use if they do an automatic assembly and soldering process. Once you know your numbers for your trace widths, for your trace spacing, for your differential impedances, the spacing for your differential pairs, your PCB stack up, the layers that your vias can go through, then you want to put all of those into your constraints. And luckily, the Cadence Orcad Constraint Manager handles all of that with the greatest of ease. And also don't forget power consumption, like how much current your traces can actually carry. So I just make sure I include all of these numbers and values inside of my constraints. All of these can be set in the PCB editor. So I set them in the PCB editor constraint manager. And that's why you want to work with good software that lets you set those constraints from the very beginning. Okay, so now that I figured out my PCB stack up, my impedances, and my constraints, the next step is to figure out the part placement. You would do your visual or graphical planning of where you want to place things based on your customers' needs and requirements, where things need to be positioned. So that's why I talked to mechanical designers, any project stakeholders, and I figured that planning out before I do anything else, before I place the first part on the PCB. Once all that's decided, make sure you place the parts. When you start placing the parts, that they're not too far apart. You don't want them too close, but you don't want them so far as well, because it would be nice to utilize as much of the space you have as possible with part placement. And again, don't place them too close so that your manufacturer doesn't have trouble assembling the parts on the PCB. Or even if you're assembling the parts, so that you don't have issues physically getting in places because they're too close to each other. Also, I placed it in such a way that I would want to keep my traces as short as possible, especially the high-speed traces, making sure they are no longer than, according to the Texas Instrument note, 5,500 mils, so 5.5 inches, no longer than that. The reason you want to make your traces short and also your vias as short as possible, in fact, you want to avoid vias entirely if you can, is so that we can get away with making our design transparent to the signals, the really fast signals that are going through the PCB. And what do I mean by transparent? It just means that depending on the rise time of the signals for your high speeds and everything, then if your trace carrying that signal is too long, it's going to start causing reflections and issues. So you want your trace to be shorter than the wavelength of the rise time of that signal. And this is just one of many techniques to make your board help the signal integrity out for free. Once part placement is optimized for improved routing, then you want to get into routing. Routing is the next phase. If you're only going up to, say, 10 gigahertz for your signal frequencies, then you can get away with some materials like your Nelco N7000 medium speed, medium loss material like I use here. I use the Texas Instruments design guidelines for high-speed signals to get me roughly in the ballpark. Okay, so if you are interested in that design guide, you can check in the link below. If I need to make any adjustments, traces, let's just say I made like the wrong calculation or something like that, or I find later, started talking to my manufacturer a little too late in the process and they said, oh, we're going to charge you a premium for going under 6 mils or something, then I can go in the impedance calculator dialog box again, and then see a list of all the traces in the design. For each trace, you can specify the trace width, dielectric material, and trace spacing. And then you want to adjust that accordingly and then update your constraints as needed. And it's really cool that this can calculate it for you. So you don't have to just do hand calculations or rely on tools outside of the Cadence software. Okay, now that's been adjusted to the recommended guidelines from Texas Instruments, we are ready to continue, because the USB traces are now within the specified range. The next step is to do your fan outs. A fan out is where you just do a short stub, the shortest stub as possible, into a via from your components that need to be routed on the opposite side. So in general, for signal integrity, you want shortest length as possible. Avoid multi-layer routing if possible, but if needed, you can use return path vias for EMI. The differential pairs are great for noise immunity, some immunity. And keeping those rules in mind, I would route my critical traces first, well, after my fanouts, then any high-speed signal traces. Depending on the PCB, you may want to route them on a 6-layer PCB internally to shield them from EMI, and also to trap or guide their electromagnetic waves coming off of those high-speed signals from traces on the top. But if you can get away with it, try to see if you can route your high-speed traces just on one layer. You also want to avoid split planes as you're routing the traces, avoid gaps in planes, also avoid major gaps inside of any copper pore. And just route up and finish the connections based on what in the schematic as well. And that's essentially routing done. Okay, after you're done routing, you're going to need to start simulating your PCBs if you don't already. But once you're done with your PCB, you want to export the ODB Plus files, not just the Gerber files, but the ODB Plus, because they have the intelligent data along with IBIS models to allow some third-party software or engineer to use their software to analyze the signal integrity of your printed circuit board. They would send the information back to you based on the simulations they ran and then tell you where there needs to be some cleanup, some fixing up, some trace adjustments, where there are issues with signal reflections and crosstalk and all that. But there is a cool feature here in Orcad Professional where you're able to take advantage of the Sigrity Aurora. If you don't have a license to Sigrity Aurora, that's fine. You just need to download and install the Sigrity Aurora software underneath your PCB Design Professional software. Once you do that, you don't need to have a license. You can go back into your Orcad PCB software and check for impedance. Okay, so it has this impedance analyzer. It's really amazing. And then this crosstalk analyzer that lets you know where your impedance has gone up. So you're able to analyze these things without needing to be a signal integrity expert or anything like that. You're able to look at where your hotspots are. You're able to see where your crosstalk is happening and adjust those accordingly. Okay, so one post-route analysis is done and finished. You would modify the printed circuit board and make some adjustments, or revise the board and do cleanup of the PCB, re-export the design files, and then repeat the process until you have high confidence in your simulations that the board will work. All right, then finally you would send the files to a manufacturer. The manufacturer may be in the 5 to 12% range as far as getting your impedances correct. So you want to make sure you're working with a manufacturer that can really hit those impedances, because that can make a huge difference. They might tell you one thing, and if you don't specify in your design notes that you need to have a specific dielectric material, dielectric constant and all that, they could pick something, or even a fiber weave that gives you a much different performance than what you simulated for. And then based on your findings from the testing and board bring up and everything, then you revise your design, and then you go through that iteration, like the second iteration, but hopefully there won't be a second iteration because you want to design right the first time. Okay, while that process works, finishing your board and exporting it for post-simulation analysis and then updating the board as needed, there is actually a faster, better, more efficient way that I like to call the look-ahead method to signal integrity analysis for PCB design. This is where you pre-simulate your board before you even start routing anything. You also do real-time analysis on your design as you are routing it, and then there's the post layout as well. So if you want to know what engineers are using to do that pre-analysis and get their boards done right the first time, then check out the next video where I show you the power of Cadence Allegro for signal integrity to only have to lay out your board once.